Hi, I'm Fariha from University of Massachusetts Amherst. This is a joint work with Suman Nath from Microsoft Research and my advisor, Professor Alexandra Meliou. Today, I'm going to talk about a data-driven debugging technique that explains why data systems fail intermittently. Data management systems and database-backed applications heavily rely on asynchronous and concurrent processing. Like other complex systems, these systems also have bugs. Bugs cause serious issues like data corruption, unresponsiveness, and crash. A notorious kind of bugs are those that manifest only intermittently. Even for the same input, an intermittently failing application sometimes fails and sometimes succeeds. The success or failure here depends not only on the input but also due to randomness of the runtime conditions such as thread scheduling and timing. And that's why intermittent bugs are hard to reproduce and very hard to debug. Our goal is to investigate the root causes of these hard to catch intermittent failures. I will now give an example of intermittent failure in NPG-SQL. It is an ADO.NET data provider for Postgres. So in NPG-SQL's Database Connection Manager module, two threads share a global array called pools. Pools keeps track of the active database connections. The variable last slot is also shared and it stores the last used index within the pools array. The find function runs in thread 1. Given a connection key, find returns its index within the pools array. For example, for key 56, find will return 2. If the key is not found, find will return null. For searching a key, find first copies the shared array into a local array. Then it searches in the local array until it finds the key or reaches the last slot index. The add function is in thread 2. Given a new key, the add function inserts the key to the pools array. For inserting the key, add first checks if the pools array is already at capacity. If there is no more room in the pools array for the new key, add doubles the pool size. It then increases last slot by 1 and stores the new key there. So let's talk about an intermittent bug in NPG-SQL. This was reported last year during May. This is how the bug happens. So find wants to find index of a key. For that, it first copies pools into local memory. Right after that, the add function in another thread adds a new key to pools, which requires resizing pools. So now last slot indicates index 5. Now when find gets back to work, it starts searching local pools. Since last slot is now 5, it will hit index 5 in the local pools. But local pools has no such index. So it will throw an array index out of bound exception and the program will crash. This issue arises only when this specific interleaving happens within the two threads. Specifically, at first, add temporally overlaps with find, which causes find to make an attempt to access an invalid array index. This causes an array index out of bound exception and it finally crashes the program. All of these events cause this failure. Now we want to identify two things. Number 1, the root cause of the failure, and number 2, an explanation that tells us how the root cause triggers the failure. In this work, we call all these runtime events predicates. There are many techniques for root cause analysis such as static and dynamic program analysis, but these are heavyweight techniques. We wanted to solve the problem in a data-driven manner because it's lightweight and generalizes to any platform. Statistical debugging is one such data-driven technique that partially addresses our problem. It reports predicates that are highly correlated with failure as potential root causes. But statistical debugging is based on just correlation, and all of us know that correlation doesn't imply causation. Specifically, there are two main limitations of statistical debugging. First, it produces a long list of correlated predicates and ultimately relies on the developer to investigate this long list of predicates manually. And second, it does not explain how a root cause triggers the failure. So in this work, we have two goals. First, to pinpoint and isolate the true root cause of the intermittent failure. And second, to connect the dots from the root cause to the failure with a set of causally connected intermediate predicates. This chain of predicates explains how the root cause triggers the failure more precisely. Now I am going to talk about how we achieve these two goals. Our approach 8 is built on 4 existing techniques and combines them in a novel way to achieve our goals. Given an application that fails intermittently, 8 first uses statistical debugging to find a list of candidate predicates. 8 then uses causality principles to make an initial guess about the causal relationships of these candidate predicates. 8 then verifies causality by actually tweaking the predicates. For tweaking predicates, 8 injects faults to the source code. To expedite root cause analysis, instead of tweaking one predicate at a time, 8 uses group testing and tweaks multiple predicates simultaneously. Based on the outcomes of one round, 8 plans for the next round. 8 repeats these steps until it pinpoints that root cause and explanation of the failure. Let's talk about finding the candidate predicates. We first instrument the source code to generate execution logs when the program executes, and from the execution logs we extract predicates. Then we use statistical debugging to find predicates that are highly correlated with the failure but rarely observed in the successful executions. 8 uses these predicates as candidates. 8's next step is to find out within the candidate predicates what is causing what. The candidate predicate set can be very large and checking all pair causal relationships is too expensive. So 8 first approximates their causal relationship. Since a cause must temporally precede an effect, we can use temporal precedence graph of the predicates to approximate their causal relationships. Since a program cannot go back in time, this graph will always be a directed acyclic graph. For example, in this temporal precedence graph, there is a path from P1 to P8, and this implies that P1 may cause P8. On the other hand, there is no path from P4 to P9, so P4 cannot cause P9. Temporal precedence is necessary for causation, but it is not sufficient. There exist many different notions for causality in the literature. But in this paper, we adapt counterfactual causality. Counterfactual causality says that if stopping an event C stops another event E, then C is a counterfactual cause of E. So how can we verify counterfactual causality? To verify counterfactual causality, we apply interventions. Intervening on a predicate alters its behavior during runtime so that it behaves exactly like the successful executions. The key idea is to check if intervening on a predicate always stops the failure. If it does, according to counterfactual causality, it is a true root cause of the failure. So how can we implement these runtime interventions? 8 uses an existing technique that injects faults to a program to make it behave in a certain way. For example, to prevent temporal overlap between find and add, 8 injects logs around both find and add to ensure their mutual exclusion during runtime. If we intervene on one predicate at a time, it will require a large amount of iterations. Since each intervention round requires going through all of these steps, this is quite expensive. To reduce the number of interventions, 8 uses group testing. So what do you do when there are not enough test kits for, say, COVID testing? Well, when testing on each individual is not feasible, group testing is an alternative and cheaper option. In group testing, instead of testing each individual, we test on groups. For example, we can mix blood samples of a group of people and then test the mixture. 8 uses adaptive group testing. In adaptive group testing, when results of an entire group is negative, we can declare that all of them have tested negative. Otherwise, we keep splitting the group until we reach certain conclusions. So what to test next is adaptively decided depending on the results of previous tests, and this reduces the number of tests required. Following this idea of adaptive group testing, 8 applies adaptive group intervention on predicates to reduce the number of intervention rounds. In traditional group testing, intervention on a group only gives information about that group, but tells nothing about the other groups. But our setting is slightly different and we have a temporal precedence graph as an extra piece of information. 8 exploits this to further prune predicates beyond traditional group testing. Trivially, if a predicate is disabled by intervention but the program still fails, that predicate cannot be the root cause. So 8 eliminates that predicate just like adaptive group testing. Further, if intervening on a predicate disables some other predicate that appear temporally later, but the failure is still there. This means that the other predicate is being caused by the predicate under intervention and has nothing to do with the actual failure. So 8 prunes these other predicates as well. But classical group testing cannot do this kind of pruning. I am done talking about the technical details of 8 and I will now proceed to present our evaluation results. We evaluated 8 on 6 real-world intermittently failing applications with different root causes. For all of them, 8 successfully found the root cause and the correct explanation. Here you can see that the number of predicates reported by statistical debugging is much more than the number of predicates in the actual causal chain. This is because statistical debugging reports many false positives, but 8 always found the predicates in the actual causal chain correctly. This chart shows the number of required interventions in adaptive group testing versus 8. 8's predicate pruning significantly reduced the number of interventions compared to adaptive group testing. Apart from the great empirical findings, we also theoretically established that 8's problem setting allows smaller search space and 8 requires much fewer interventions than traditional adaptive group testing and a lower information theoretic lower bound. Please refer to our paper for more details on this. To summarize, 8 is a data-driven technique for debugging intermittent failures. It produces causally verified root cause and explanation chain of intermittent failures. 8 is more accurate than statistical debugging and more efficient than classical adaptive group testing. Thank you for listening. We'll be happy to answer any question through the communication channel.